Hello everyone, welcome to Emerging Tech Bytes. My name is Sonal Parekh. I work for Cisco Systems. As a part of this series, we are learning 5G from the scratch. This is our second session. The first session is already available on YouTube, and now today we are going with this second session. So I highly encourage, if you haven't looked at the first session, please go and watch that before you proceed with this session, because there are many elements which are connected, or we are connecting the dots with that previous session. So this was the slide where we ended our last section, where I showed you like what all domains are there for 5G that makes a complete 5G network. So we have the user equipments, which is called as UE. In 4G as well, it was called as UE, which is nothing but just your endpoints, cell phones, or any other type of sensors. And then we have this radio access network and the mobile core network. And to interconnect these pieces to radio to the device, we have spectrum. And the core network to the RAN, we have this transport network. And I promise that we will open up these in the subsequent sessions. So today we will be going through some of the components of this. But before I get into those, in any typical service provider, there are different teams who takes care of different technologies that you see in this picture. So for example, the RAN or the uh, mobility core can be taken care by the mobility team, or most of the time the RAN is outsourced to certain vendors. Then we have this transport network, which is managed by the SP core team, which manage the backbone network basically. So all those fiber-based backbone networks between the tier 1 or tier 2 cities that you see, that comes under core network. And this, please don't get confused with this core network and this core. This is mobility core, where you have all the core components of the mobility. We will talk about those in subsequent sessions, but this one is where you are handling the backbone network of the SP. So coming back to our discussion, today we will be opening up this picture from the left side. So we will be talking about the UEs. And to be honest, there is not much to talk about UEs, but we will be covering some part of it as what makes a UE 5G compatible. We will be looking at the spectrum piece. This is actually a key ingredient, as we looked in the last session as well, and about some of the capabilities enhancements for the RAN as well. What makes 5G RAN a 5G RAN? So with that, let's get into the agenda. So this will be our focus for today's call. So now let's go to the agenda. As I was saying, we will look at the 5G device ecosystem. I will cover at a high level what are the deployment options. Then the spectrum overview. How does the spectrum allocation policy work across the world, and what had changed in 5G? And then we will be looking at some of the new radios key technologies. So in the RAN world, 5G radio is called as NR or new radio. So for the device ecosystem, there is nothing much that we can talk about here because these are the product-based company who make their devices 5G compatible. There are number of 5G devices that are continue to rise, and now I was looking at this GSA 5G device ecosystem report, which is available online on their website. This count has passed more than 1,000 already. And the major chunk that you will see first in the market is around cell phones. There are already a lot of cell phones are there which are 5G compatible. Then we have the laptops with the 5G connectivity. But if you recall our first session where we were talking about 5G, not only focused on the end users, it was also focused on the enterprises. So this is where we are connecting our dot. So the enterprises are mainly interested in the 5G modules and the hotspots or CPEs. These 5G modules are nothing but it enables a sensor to connect to 5G and deliver the data to its application layer. And that app is having some business critical insight that this enterprise is using. So with those modules that we have in those sensors are actually communicating with the 5G. So this is what, as I was saying, there is nothing much that we can cover here. These are the endpoint devices, which being an individual user, you buy it from a manufacturer like Samsung or Apple or OnePlus or any other smartphone. Or if it is some 5G modules, there are manufacturers available who sell it to the enterprises. Now let's look at what are the deployment options that are available. So mainly there are two deployment options that exist. One of them is standalone, another one is non-standalone for 5G. What I mean by that is, if you look at this picture, we have our EPC, which is nothing but just the 4G core component, 4G core component of 4G. Again, core, RAN, UE. So this is that core part. Then we have the EUtron, which is basically the RAN part for 4G. And finally, we have this endpoint. So this endpoint is connecting to this E node B, which is acting as a master here. And then this is also connected to the G node B, which is a secondary node. So G node B is 5G and E node B is for the 4G. So here your 4G E node B in the access network is acting as a master, whereas the G node B is acting as a secondary node. Rest all the components, whatever you see in the core, are 4G. So this type of deployment where you are moving your access network, your radio network to the G node B, and at the same time, all the control plane signaling still stays with this E node B, is a type of non-standalone deployment. There is another option exists in this where you have this core network where you have migrated your core network, let's say to 5G. So this is your 5G core, but still your master is E node B. So your access is still E node B, and you have started introducing the G node Bs into the network. So E node B is the primary node, the master node, which is responsible for the control plane and data plane. And this green channel in both the cases is used for the data. So this is control plane, and this can be used for the data plane. Let's. So this is actually your non-standalone deployment where you have the 4G core or the 5G core, but your access is still working on the 4G. It's the E node B is acting as a master, and you have these dual connectivity where you are getting more throughput. So you can use this channel also for the data. So in this way, it is serving the dual connectivity, and you get more throughput. Another advantage of this is that before you or any operator is going, let's say, with the full-fledged deployment, they have an option to serve their end customers with the 5G, with this G Node B. So they are leveraging all the benefits of 5G without even going fully fledged with the 5G network. So that way your end users are getting more throughput, and you are offering them the 5G services, and you are slowly upgrading your core network to 5G core, and maybe moving away from the E node B deployments slowly. So that is the non-standalone. Now, if we look at the standalone deployment, in this you have your 5G core, then you have your next gen RAN, and your master node. This is the point to note here. The master here is G node B, which was not the case with these two. Here, the G node B was secondary, if you see. So your master is G node B. So now the 5G network has started taking over. And then you have a secondary E node B or a G node B, which is serving that endpoint. So your endpoint is still have these two connections. Now the control plane is also shifted to the master G node B. But in this case, you have this G node B serving, but at the same time, you have a secondary G node B or E node B. But what is the purpose for that? That is just to have more throughput. So this is this scenario that you see here, we call it as DC or dual connectivity. We will see the benefit of dual connectivity in the later slide. But for now, just understand that non-standalone, your master is acting as an E node B. And by the way, just one more tip here. If this is 5G core network, then this E node B that you see here will be enhanced E node B. I was not able to write it properly due to some issues, but this is enhanced E node B in case you have 5G core network. And then in the standalone, this master node is taking over. So now let's move our focus from these deployment options to the type of spectrum. So there is these three type of spectrum that you see is available in 5G. The low band, which is FR1, mid band, again FR1, and high band, which is MM wave or FR2. So the low band spectrum is available for to cover the large area. So whenever we talk about spectrum, there are few things that we need to look at. One is the coverage, then the throughput, and finally the bandwidth, how much bandwidth it is serving. So if you go with the low band, as you see orange here, it has a wide range. This range in the spectrum can cover several kilometers, and it can even penetrate the buildings. Let's say there are multiple floors in the building, so it can even penetrate the walls or the rocks. So if you have a 5G deployment where you want to cover a larger distance where there are so many buildings are coming, this low band comes really handy where it has an ability to penetrate through the walls. So the coverage wise, this low band is good. So we will give it as like G. So this is a good from coverage perspective. But from the throughput perspective or the bandwidth perspective, it is not that great. So it can carry up to like 300 Mbps of data. So the throughput is low for this. Then we come to the mid band, which is this sub 6 gigahertz of the range, which is, by the way, one of the popular uh, range as well for 5G. So in the mid band, it has less penetration power or coverage power as compared to the low band, but then it has higher throughput. So for the area perspective, it has less coverage from area side, but then it can support up to 1 to 2 gig of bandwidth. And the throughput is good in this case where you are getting this. Finally, we will come to this MM band. MM band is this green circle that you see here. The distance is very less. It is even like somewhere around few meters to 1 or 2 kilometers. That's it. And this range of spectrum cannot penetrate through walls or any obstacles and all. But at the same time, while the coverage is low, I am writing that here just because of the less space here. So the coverage, I am writing that as a C, coverage is low, but throughput or the bandwidth, you get anywhere between 10 Gbps plus. So you get very high bandwidth when you go with this wave spectrum. So these are the three range that you see are available for 5G, and it's available for the providers where they can get it via the auction. So now, if you recall this slide, I have talked about this slide in the first session where I had shown you that 5G is designed to achieve these numbers: 10 Gbps, 1 millisecond latency, 100x download, very dense network, right? So with these three range of the spectrum, as I was saying earlier, that for the most of the cases, 5G will not support all of these things at the same time. So then we need to deploy 5G and tailor it to our specific need. So if you need like very high bandwidth in the order of 10 Gbps or something, you need to go with waves. But the problem with these waves is they cannot travel far distance. So there has to be there is a problem, or there is this much talked about concept in 5G about densification. So where you will have like more and more towers if you want to fulfill this high bandwidth use case. But then the mid band and the lower band, we have an advantage of wider coverage. Or mid band is like the midway between the two, where it's travel up to certain distance and at the same time it have a good throughput as well. So with this, uh, this is the range for the spectrum. So below 1 gigahertz, which we call as low band. So this have, as we had seen, that wide area coverage, excellent building penetration, and then it is low on the bandwidth side. So bandwidth capacity that you will see here, as we were talking, is like 300 Mbps only. Another thing is that there are limited spectrum availability in this band, because there are not many wireless applications that work below 1 gigahertz. So the spectrum availability is less. Then we have this mid band, which is 1 to 6 gigahertz. So it offers good coverage, good spectrum availability as well in this segment, and we can get anywhere between 1 to 2 Gbps of data. And then anything beyond this is like high band and FR2 as well. You can call it FR2. These two are FR1. So this is low range, but it supports lots and lots and lots of bandwidth, as we had seen, but it cannot travel further. So now let's just have a look at the spectrum allocation policy around the world. So with the from the previous generations to this generation, there are few things which are changing. Earlier, whenever an enterprise want to deploy 5G services, they were supposed to connect with their telecom service providers. So the service provider is the one who had taken some licensed spectrum from the government. So the spectrum is licensed and taken from the government, and then they can further give it, lease it, or provide connectivity services to the enterprise. But with the 5G, what we are seeing is the enterprises, the large enterprises, are directly getting some range of spectrum for their private consumption from the government directly by paying them a nominal fees. Again, I want to reiterate that I'm saying that enterprises are getting this spectrum directly from the government for their private consumption only. So, for example, in Germany, we see that the 3.7 gigahertz of spectrum is available for private consumption. Enterprise can get somewhere like 100 megahertz, which is enough to cover a large site for the private consumption. But then these spectrums are confined to certain geographical locations. So they cannot be used for public purpose. It is just for that enterprise dedicated cellular network. And this we actually called as private 5G, 5G network. So this can be a separate talk itself, but private 5G is nothing but what you saw all those three domains, right? UE, the RAN, and the core network, and then interconnecting pieces. All of those pieces are deployed dedicatedly for an enterprise. Let's say there are different models that exist, but we will cover that maybe in some future session, not as a part of this series because that's a different topic. So these spectrum, as I was saying, are available for private use. In fact, multiple countries, for example, Germany, Japan, Hong Kong, and there are some more countries which follow this strategy where this certain range of the spectrum is available for direct consumption to the enterprise. And in APJC, the new thing that we are seeing is that the spectrum is available in the wave segment as well. So if I go back to the slide, as you see, right, 1 to 6 gigahertz is like the mid band, and anything beyond like in the high range, 24 gigahertz, 25 gigahertz, 27, 28 gigahertz, that's like the wave segment. So in this, you see here, this is the high band spectrum. So this spectrum is local, consumed by that private entity. Then there is something called as shared spectrum as well. So in the US, there is a different approach that US took while distributing the spectrum. So there is something called CBRS, which is Citizen Broadband Radio Services. So they came up with a spectrum range and then they auctioned it. In that, telcos took part, but at the same time, enterprises have also taken part into that. So enterprises can get some shares of their spectrum as a part of shared this CBRS range. So that the only difference between other countries where it was only meant for private consumptions by the enterprise, CBRS is something that even telco took part into it. They also acquired some spectrum, and at the same time, enterprises had also got their share into it. And these are, like geographically confined. So you can, let's say, you have a mine which is somewhere like 5 miles away from the city. You don't have any network there. You can have this private network without much fear of interference because there is nothing nearby. So with that, let's move our focus around some of the key technology features which actually enhance the data rate that we are talking about or the quality of the 5G network that we are talking about. Right? So there are certain key features. Again, that is not all. I'm just covering few of them as a part of this lecture. Some more will come in the next session. So we will be looking at dual connectivity, small cells, the spectrum. We have already looked at it, but we will see a bit more into this. OFDMA, which is actually the physical layer, let's say, between your radio to UE. How does the frequency travels? So that is the OFDMA, and then we will cover the Cloud RAN part. So the first part that we had seen is as a part of this is the dual connectivity. And we have already seen dual connectivity while discussing about the deployment of 5G SA or NSA. So here in this case, there is this one E node B, let's say in this case, is acting as a master and the other is acting as a secondary node. And this master node is actually deciding what type of data to be delivered, the quality of service that is committed for this endpoint. And then the secondary node is just for the data communication. So here we can see that this endpoint is actually enjoying dual connectivity. That way, can have increased data rate. And there are many options exist, as we had seen, like you have master E node B, then secondary G node B, which is your NSA, non-standalone, or you can have a master G node B and secondary E node B or G node B, that is your SA. So this is your SA network, this is your NSA network. Now, if you recall in like NSA discussion, I had also talked about very briefly about this G node B connecting, right? I can understand that, okay, E node B, because you have those 4G network up and running, and that's the reason you are introducing these new G node Bs and connecting, and slowly you have a migration plan towards this standalone deployment. But what is the purpose of this G node B? Why we are connecting a secondary G node B, let's say? One is this dual connectivity help us to deliver faster uplink and downlink data rates for the end users, that is for sure. But then recently, uh, there are two companies called MediaTek and Ericsson have done some tests where they connected a single device to both a mid-band spectrum and a high-band spectrum using dual connectivity. So you see, right, mid-band and high-band, as we have covered in the last like few minutes back. So this dual connectivity, so mid-band was used for a broader reach, high band was used for higher bandwidth. So this dual connectivity, as you see, is broader, is coupled with the broader reach of the mid band. So we are getting the benefits both ways. So it was the first time that the standalone 5G was tested with mid band and this high band. And this was according to Ericsson, where they were able to achieve higher data rate along with it. So the point I'm trying to say here is that you can combine the spectrums with these dual connectivity options. Now let's look at the other feature uh, for the 5G, which is small cells. So we talked about this wave, and we had seen that we have very minimal coverage around it. So what could be the solution? One is like you have all these massive towers installed everywhere in the city, but that doesn't scale well. So there is something called small cells, which are like very low powered radio access nodes that have a range somewhere from 10 meters to few kilometers. I already have some pictures from this Wikipedia link, so you can uh, have a look and visit this Wikipedia page as well if you want. And you just search small cells on internet, and this link will pop up. So how does this help us to have the better connectivity in terms of throughput? So what basically we do is we have these small cells spread across a certain area. They have their coverage area. Now a endpoint is there. Let me take a different color pen here. Then we have this macro tower. So with the dual connectivity, this endpoint is connected here as well as to this macro tower as well for any control plane connectivity. For the data plane, it can use this. And when this endpoint move, let's say it comes to this circle, it connects with this cell while keeping its connection intact with this macro tower. And the same goes when it moves to third or fourth small cell. So that's the advantage as you see with the small cells along with the dual connectivity. Now, let's just move on towards the frequency part. So this we have already visited, but these are the numbers for NFR1 range, which cover your low band and mid band. And then this FR2 is your high band or MM band. So MM wave is from 24.2 to 52.6 gigahertz, the range. Okay, so this is the operatable frequency range for 5G. Before we go at this physical layer of OFDMA, let me talk about some of the basics here. The frequency, what is actually frequency? Frequency is one of the most misunderstood field when we talk about these wireless students in the class, and many times they can't even visualize it. So let me try to give you a perspective here. So you see that you have this ball which you are bouncing back and forth. Okay. So this ball is like bouncing back and forth that you are doing in this direction. Now, if you want to plot it against the height, which we measure by h, and the time, it basically the graph will come something like this. This these small curves that you are seeing here, that our ball will go like this. Okay. So this actually forms a pattern as you see here. So in this pattern, on the x-axis we have time, on the y-axis we have the height. So if we cover like let's say the time, if we plot, so let's say this is 0 second, then here we have 1 second, here we have 2 second, 3 second, 4 second, and goes on. So from 0 to 1, you see that this is actually covering just half of it, half of the cycle, from here till here. So this we call in terms of units for frequency is 0.5 hertz. Hertz is the unit for frequency. And, and in some cases, you will see that within 1 second, it completes its whole cycle. Or it can start other as well. If we talk about like frequencies in the range of kilohertz, megahertz, or gigahertz, that means such cycles, as you see, millions millions of cycles that are getting completed within that 1 seconds of time. Okay? That's why if you look at recall the previous discussion in the high band, we call it as a millimeter wave. So those are like very small that can like millions or maybe billions of cycles that it can complete, or one such complete cycle it can complete within that 1 second of duration. And then if we look at the human voice, that human voice have a range of somewhere around 80 to 280 hertz. So if we want to use this range, 80 to 280 hertz of the range in the wireless communication, it basically does not have any use because this is deteriorate with the distance that it travels. So for that, we have a concept of called, I mean, this is very basic, so that's why I'm just covering it at a very high level, just so that you can connect the dots. Uh, Now this is the base to understand OFDMA, but for 5G, it's not like directly related. This is just the basic, the base layer. So if we want our voice to travel a larger distance, we put it on something called as carrier frequency, carrier wave, let's say. So our voice, with the help of modulation, if you have here the term frequency modulation, ride on this carrier wave and actually travel the larger distance. Okay. So now coming back to OFDMA, in case of OFDMA, what we do is, so there are these multiple carriers. We can call it subcarriers. So these multiple subcarriers, so there is this one carrier which you see here in blue. Then there is this another carrier which you see in green, and another carrier in orange. So there are these multiple carriers, and they travel together. So OFDMA is orthogonal frequency division multiplexing. What it means is, when this one, the blue, is on its peak, so this is called as peak, rest all of them are at 0. Same way, when the green goes to peak, the blue comes to 0, and at the same time, the orange also comes to 0. So this is how your OFDMA work at a high level. And then you see this gap here, that is between the gap between the two peaks, is called as delta F. This is actually the spacing. So 5G NR, the 5G new radio, actually uses OFDMA, as was the case with 4G as well. So 4G was also using the same range. The only difference is, since 5G have a wider range of frequency, this delta F can cause some issue. So what we do is, for 4G, this spacing was fixed around 15 kilohertz. So this distance that you see here was a fixed distance, but in case of 5G, it is scalable. So there is a formula. We are not going into the depth of that formula, but for you to understand it at a very high level, 5G uses this scalable carrier spacing so that it doesn't cause any issues while using OFDMAs. Okay. So now moving on to the cloud RAN part, and this is where we will like end our today's lecture. So the cloud RAN in the CRAN technology, basically for the G node B, there are two pieces. One is the CU, another one is DU. Centralized unit is then the distributed unit. Think of a scenario where you have so many endpoints which are being served by a DU. Uh, so this DU, and then we have this DU. So let's say this DU is serving this DU is serving these two. And then at the back end, you have this centralized G node B, which is connected to all the distributed units. So this centralized G node B is responsible for the scheduling, the security, basically all the encryptions that happened, as well as the power management to avoid any kind of interference. While this distributed unit is only responsible for transmit and receiving the data. So that way you have split the control plane and the data plane functionality. The control plane is a centralized piece which can connect to multiple distributed units. The advantage is this provide much more scalable way. In case there are more DUs which are coming, we can easily scale this, or we can downscale this also if there are like these DUs are going away. So on-demand resource allocation is happening in this case, and it also provides some reduced cost benefit as well in this. So basically, as a part of Cloud RAN, you are separating the CU from the DU. So these are some of the technologies that we have covered as a 5G NR. What makes the 5G as efficient as we were seeing in those numbers. Now, in the next session, we will be talking about the massive MIMO, the beamforming, and then we will reuse the same diagram and open the core domain of it, what all pieces goes into the core. So we are concluding our today's session here. Would like to say thanks for joining this and happy learning.